Hey everyone, welcome back. We're starting section 2.2 where we talk about summarizing the shape and center of one quantitative variable. So we've talked about one categorical variable, two categorical variables. Here we're going to start talking about one quantitative variable. Our first example is an example we've looked at before, or a data set we've referenced. It's the Hollywood Movies data set. The graph you see below is called a dot plot, and it shows the world gross income from all viewers in millions of dollars of all the movies to come out of Hollywood in 2011. So the values on the horizontal axis are the dollars in millions, and each dot is a movie. Are the movie incomes categorical or quantitative? Well, since they are dollar amounts, clearly quantitative. Millions of dollars. Now it says to describe the shape of the distribution. So if you have taken statistics before, you may know some words that describe the shape, but before we talk about what those words are, I just want to kind of describe it more casually, which is the data is kind of shifted to one side, right? The data is all kind of piled up on the left, and it tails off to the right. Right, so when you have this kind of shape where most of the data is kind of shoved over to the left like this, they're kind of like a pile of data that's not centered but pushed over to the left, and it has what we call a right tail. This distribution is called right skewed. So it's the side that the tail is on is the direction that the tail is going is the direction that we give the skew. Does it appear there are any outliers? It doesn't really explain what outliers mean, but I think it's supposed to represent values that are like noticeably different than the others. And I think these three seem to kind of just be in a class of their own. They're a bit larger than all of the other movies, so I'm going to call those outliers. So these three movies made a bit more money than all the rest. Okay, let's do some definitions. So in a histogram, this is going to be a graph that we look at in a minute. The height of each bar corresponds to the number of cases within the range of the variable, within that range of the variable. In a dot plot, which is what we see above, each case is represented by a dot and the dots are stacked. And an outlier is an observed value that is notably distinct or different from the other values in the data set. Now a histogram, we haven't seen one yet. I'll just peek ahead, we can take a look. There are some histograms. So each bar tells you how many cases are in that the range of that variable. So notice they do kind of remind us maybe of a bar chart in the sense, but a bar chart is for categorical data and a histogram is for quantitative data. So remember, in the categorical sense, when we're doing a bar chart, there's no numeric scale on the bottom. We just list the categories in any order we feel like, and it's fine. But in a histogram, it's quantitative, so the horizontal axis is numeric, which means there's an inherent order to the values that we have there. It's valued according to the usual way that numbers are valued. Histograms and dot plots both will tell us about the shape of a distribution, whether it's symmetric, which means kind of the same as to the left as to the right, whether it's skewed right or skewed left, and we use this term called bell-shaped because we see a lot of distributions that kind of have a shape like this, which we call a bell. So that's what histograms and dot plots are going to show us that just by looking at them, they can tell us that, whereas a data set we might not be able to tell just by looking at a bunch of numbers. These pictures can give us more information. So here are some examples. We have a symmetric distribution on the left. The middle one is a right skewed, which is like the example 1, except it's a histogram instead of a dot plot. And then there's a left skewed example on the right, where the data is kind of shoved over to the right, and there's a little kind of a left. It's kind of a stumpy tail on the left, but a tail nonetheless. Okay, so there's two main ways that we describe the center of a distribution. The first is the mean of a distribution, which is also called the average. Most of us are very familiar with this calculation. And the way you calculate it is you add up all of your data values. So in my example up here, I have n data values, and then you divide by that the number of data values that you have. So x1, x2, etc. These are data values. So I'm basically just saying we add them all up and we divide by how many we have. There's another more compact way to write this. You've taken pre-calc or something like this. You may know this notation. So that's just, the numerator is just a compact way of saying we add up all of the data values from 1 to n. If you have never seen that before, that's okay. You don't need to know that. The median of the distribution is the middle value of the data set when the data set is ordered. So we need to order the data first, and then we find the middle value. So when there are an odd number of numbers in your data set, there will be a single number in the middle. So when two values are at the center, this would be when you have an even number of numbers. If we have an even number of values, we take the average of the center, of the middle two numbers. Because if you have an even number of numbers, you're going to have two numbers in the middle. Okay, and we'll do an exercise, and pretty soon here you'll see how that works. Some notation, the sample size, we denote by n, a lowercase n usually. The sample mean is x with a bar over the top, or a line. We say x bar. If your population, if your mean is coming from a population, you do this Greek letter, which is pronounced mu. Some people write it mu, but you pronounce it as like a cat, mu. And that's our notation for a population mean. All right, let's practice calculating a mean and a median. We have the number of ants climbing on a piece of peanut butter sandwich left on the ground near an anthill for a few minutes was measured at 7 different times. The results are here. Calculate the mean number of ants and then the median. So we'll just pause and try this, see if we come up with the same answers, and then press play when you're done. All right, so we know the mean number of ants is just a matter of adding all the data values up and then dividing by the number of values. So there are 7 values here. We would call this x bar as a notation, and then we add. And then I round that to 35.9. Okay, and then the median. So the median is the center value, right? But remember, we have to order them first. So I order them from least to greatest, and then I note the center value is 36. That's the median. All right, so notice the mean and the median very, very close. So it wouldn't really matter if we used the mean or the median to describe the center here. That would both be about 36. But suppose one of the sandwich bits was extremely appealing to the ants, and instead of 59, the number of ants was actually 159 for that value. So we're going to change 59 to 159. And then we're going to do the same calculations. All right, so go ahead, pause and try, and see how our situation has changed. And then press play when you're done. Well, the new average here is 351 over 7. So I actually just added 100 to my value from number 1 because we have 100 more ants overall. And I divide that by 7 and I get 50.1. But the median is unchanged. How do I know that? Well, I could just look at the number 2, and if you put number 1 there, and change 59 to 159, that doesn't change the median at all. If you just change the largest value, in this case, from 59 to 159, nothing changes. So now we have a case where the mean and the median are not similar. And so we kind of have a decision to make if we're just going to report one of these numbers. Which one of these numbers seems to be a better description of the typical number of ants that you find on the sandwich? I would say that 36 is a better measurement of that. Why is that? Well, if you try to say 50 is typical, 50 is actually larger than every single value except the very biggest one. So it's hard to really use that as a typical number. Whereas 36 still kind of describes the typical number, and you just say, well, one of them was really much higher than the others, but typically it was 36. So sometimes we like to report the median as the typical value, and that's when we have outliers, like 159 would be an outlier, or if your data is skewed, sometimes we like to report the median. Okay, so let's look at example 4. It says to look again at the dot plot of world gross income. Okay, there's that. And then it says to estimate the median. So remember, the median is the center value. So we kind of want to pick a value so that there are just as many values to the left of the value we pick as to the right. So it looks like there's maybe, 100 or so dots here. I'm just going to maybe like right in here, so that I'm saying that the number of dots here is probably pretty similar to the number of dots over there. So that looks like it's about 100. It's a really rough estimate. If I wanted to be better, I could count the number of dots and make sure the median was exactly in the middle. So it's about 100 million. Now they ask us, do you expect the mean to be greater than or less than that value? So let's think about that. Let's look back at the picture. All right, so if the data was kind of symmetric around this point, somewhat like this, I would say the mean and the median would probably be pretty similar. But the values on the right side extend far beyond the median, right? Whereas the values to the left of the median are all kind of near the median. So the more those values stretch out to the right of the median, the more the mean is going to be pulled in that direction, right? If we add larger and larger numbers, we're going to move the mean over. But as we saw in the ant example, you can change the values, the maximum value. I could change this to 159 or 1,159, or I could keep adding ones. I could put a couple zeros there. The median doesn't change, right? But the mean certainly would if I did all that. The mean would certainly change. So we expect the mean to be larger. The mean should be greater than, because of I would say two things, because of the right skew and the larger outliers. So outliers can move the mean, but they do not move the median. We call the median a resistant statistic because it is relatively unaffected by extreme values. So the median is resistant while the mean is not. The mean is very sensitive to outliers. Okay, so when using statistics that are not resistant to outliers, stop and think about whether the outlier is a mistake. Sometimes that's the case. If not, you have to decide whether the outlier is part of the population that you're interested in measuring or not. Usually for outliers that are not a mistake, it's best to run the computations twice, once with the outlier and once not, and then you just report both of those. The reader can see how much the outliers are affecting the calculations. All right, so that's all the videos for 2.2, and I'll see you in the next video, section 2.3.